Hello, hello. So today we are talking about the goodness of fit test. This is one of the chi-squared tests. Chi-squared is different than all the other significance tests we've done. It follows the same format like you'll see because it deals with categorical variables instead of numerical ones like we've been working with. So what is chi-squared? We call this chi-squared, not chi-squared. It's chi-squared. And it's notated as an x squared. So sometimes you'll see it like a fancy x. If it's in your textbook or another handout, it may look like a fancy x, but if you just do x squared, we know it's chi-squared. So there are three types of chi-squared. The first one is called goodness of fit, and this is what we're working with today, the goodness of fit test. There's two other tests, one for two-way tables and one for independence, and we'll talk about those next class or in future classes. So the goal of chi-squared, kind of what this test is doing, is we want to see, is there a relationship between two categorical variables? Is there some connection or association between variables, or are they independent? So chi-square test for goodness of fit, we're doing the goodness of fit test today, is a single test to determine if an observed sample, so if what we see is significantly different from what's expected or hypothesized. So we're going to be comparing what we see when we collect data and seeing, is that different than what's hypothesized or expected? So the test is based on data counts. This is going to be important. You're going to be using whole numbers, not proportions. So you don't want percents or decimals. You're going to want whole number data counts, and you'll see that as we go through the problem. Also, the more the observed, or the more of what we see, the more that differs from the expected, the more evidence we have to reject the null hypothesis. Which makes sense. If I see things that are really different than what's expected, I think the null hypothesis or the equals claim is wrong. So before we kind of look at a test and look at an example, let's just take a look at this curve. This is the chi-squared curve. It's not normal. It follows this really skewed to the right look, but chi-squared is kind of a marking on that curve, and the p-value is everything above. So it's still that concept of a test statistic and a p-value, but the curve is skewed to the right. It's not normal. So there's a 4-step process for how to conduct a chi-square test. It's still, the state, plan, do, conclude steps. State is the exact same. Conclude is the exact same, but the plan and the do are a little bit different. And we're going to talk about the plan a little bit more in this video, but we also talked about it in class. The first thing in the plan step is they have to be random samples. And that's pretty standard. We've been using the random sample condition for a while. The second plan step is that all of the expected counts must be greater than 5. So when we calculate the expected counts, you're going to see kind of how we find those. If you want to do a little mark, expected counts equal n times p, and that's what we saw in class, and we'll see it again in the video. But they have to be greater than 5. The do step, we have the test statistic chi-squared. We have to show our degrees of freedom, and then we have to do a sketch where we show the p-value. So we're going to take a look at the state, plan, and do steps today. So firstly is state. What are my two hypotheses? Your hypotheses will always follow this pattern for goodness of fit. The null hypothesis is that the population proportions are equal to the hypothesized value. So the population is the same or is no different than the hypothesis or the hypothesized value or the expected counts. The expected value. Ooh, my E's are not showing up. There we go. Oops. Okay. There, okay, good enough. Okay. The alternative is that at least one of the population proportions is different than the expected value. So the null is always equal, and the alternative is that at least one is different, which brings us to key point number 1. The null hypothesis is always the hypothesis that states there's no difference or that things are equal. We should be really comfortable with that kind of mindset that the null means 0. It means there's 0 difference or no difference, or that the claim equals what's actually happening in the population. So let's take a look at an example. And this is going to be our example for this video, so make sure you get down this table. You need this table, and we're going to be adding to this table a little bit. So leave a little room below. So it says a market research firm wants to know if there is an obvious leader among the 5 most popular manufacturers of laptop computers, or whether they are all about equally popular. They ask a random sample of 250 people which brand of computer they trust the most. Here are the results. So it gives us the trusted brand. It has Apple, Lenovo, Asus, Dell, and Toshiba. And then it has their frequency. This is where I was talking about the whole numbers. These are going to be whole number values, not percents or not decimals. So first state, I have to have my population. Oops. And the population is all the people who use laptop computers, or all people who they could have surveyed. The parameter, or what I'm measuring, is there an obvious leader among manufacturers of laptop computers? Or, kind of in general speak, is there a preference in laptop manufacturers? The null hypothesis is always the no difference one. So there is no difference in laptop preference. The alternative would be that at least one of the laptop manufacturers is preferred or is different than the others. So at least one of these brands is preferred over the others is my alternative. So then we get to the plan step. Well, the first one is the sample random? It says random sample of 250, so check. The second part of the plan, are all the expected counts greater than 5? Well, how I find my expected counts equals the sample size times the probability that they're all equal, or the probabilities given to us in the problem. Well, the sample size is 250, and if I have 5 manufacturers, if they're all the same, P, or the probability that you'd like one over the other, would be 1/5. Well, that gives me 50. So all of the expected counts are the same in this problem because there was an equal chance, or 1 out of 5 chance. So the expected counts are 50, which are greater than 5, so that condition's met. So the expected counts come from the sample size times the probability that that category is chosen, which in this case would be 1 out of 5th because there were 5 categories. Well, then I get to the calculations of chi-squared, and we saw this formula in class, so this formula is very familiar to us because we broke it down. But just to rephrase, it's the sum of all of the observed minus the expected squared divided by the expected. So let's take a look at filling in this table. So this is the table that we've been working with. I just added a total column, and then I added an expected column below the observed one. So if I want to find chi-squared, how I do that is I take the observed minus the expected squared divided by the expected for each of these categories, and I add them together. So I would add Apple with Lenovo, and so on until it looked like this. So I have all of my components down here. We call these little boxes components. And when I do all of these in my calculator one at a time and I add them together, I get chi-squared, which is this box right here, which is 8.2. So how I got that is I found each of those components, I added them together, and it gave me 8.2. And this value is chi-squared. So the first part of my do step we already did on the last page. That's to calculate chi-squared. So step 1 is to calculate chi-squared, which we said are adding all these boxes together. And then the sum gave us 8.2, which was chi-squared. The second part of my do step is going to be to sketch the chi-squared curve, and the third step is to find the p-value. So what is chi-squared? Chi-squared looks like these curves. They're very skewed to the right. And to know which row to use on the chi-squared table, I need to find my degrees of freedom. Well, the degrees of freedom is not n minus 1. It's actually going to be k minus 1, where k is the number of categories, not the sample size. So it's the number of categories minus 1 is my degrees of freedom, or df equals k minus 1, where k is the categories. You can see the bigger my degrees of freedom get, the less skewed, or the more or the less unimodal, the lower the peak gets on my chi-squared curve. So once I find my degrees of freedom, I get to use this chi-squared table, and you guys either got this or will get this if you weren't in class. So the chi-squared table has degrees of freedom. It looks very similar to the T-star table, so make sure you're using the chi-squared one. Well, if I think about my example, df is k minus 1, where k is the number of categories. I had 5 different laptop providers. So my degrees of freedom equals 4. So I know I'm looking in this row of 4 right here. This is the row that I am going to look for my chi-squared value in. Well, my chi-squared value, we said, was 8.2. So just like with T-star, I want to look in this row and see where my in between, or where's 8.2 in between? And 8.2 is in between 7.78 and 9.49, or my p-value is in between 0.05 and 0.10. This is how I find my p, and I find my sketch of chi-squared. So this is the second and third part of the do step. I'm going to sketch my chi-squared curve. So it doesn't have to be beautiful. It just has to be skewed to the right. So on my curve, I'm marking 8.2 because chi-squared equaled 8.2. And then my p-value is everything up here. Well, if I use the table, I just find the range for my p-value. And from that table, I know that my p-value is going to be less than or smaller than 10% or 0.10, but bigger than 0.05 or 5%. It was in between that range, and that's how I find my p-value. It's the shaded area above chi-squared, and it's going to be a range if I use my table, and the range for this one was in between 5% and 10%, because 8.2 was in between the 7 number and the 9 number. So that's my second key point. Calculate chi-square by adding the last row of the table. And the p-value comes from the table and degrees of freedom of k minus 1. So that's a wrap. We use a goodness of fit test to determine if there is a relationship between two categorical variables. This is section 11.1 in your textbook. Please go there for more examples and your homework problems. Thanks, and I'll see you next time.